Good morning, everybody. We would like to thank all of you who are watching. I know we have right now over 300 participants from 33 countries. So welcome to Quantum Battles in Auto Science. This has been a challenge to us to put together, and we hope you enjoy the conference. This is a different format and also a virtual conference in the middle of a pandemic. And we are going to start our first session now. We're going to spend 3 days looking at key issues in auto science at the quantum auto interface. So the first day is going to be tunneling decoherence. Second day is going to be quantum interference and electron-electron correlation. Third day is going to be the future and analytical versus numerical methods. So we're going to start now our first session on tunneling. So we have distinguished speakers from everywhere in the world. And our first speaker is going to be Jan-Michel Rost. So I hope you enjoy the conference, and let's start.
Yeah, Carla, thank you very much. So really big thanks to you and all your colleagues going through that and taking basically the effort to organize this as a virtual meeting. I guess we really appreciate that. And we hope it will be very entertaining and informative. And I guess we are more hungry for new science in form of conferences than we usually are, since we don't travel as much. And it's just great to have this. So let's see if it works well. So I will now try to share my screen with you. And this is going to be here. Let's see it. Share. Sharing the screen. Well, this does not seem to work. It worked before. Hang on, why doesn't it work? So can you see it? No, let's try it again. Okay, share screen. Oh, very strange. I'm sorry for that.
We are able to see your screen if you start the presentation.
Oh, you are? Okay, yeah. Perfect.
Great.
Perfect. So yeah, so sorry for that. So I want to talk about timing ultra-fast processes and non-adiabaticity. It's quantum battles, so it should be a little bit controversial, I guess. And so I will not talk mainly about tunneling, just a brief primer, also I guess for the battles afterwards. But we have essentially two wonderful techniques right now to time ultra-fast processes. One is the Attoclock, which is essentially elliptical polarization pulses for photoionization, mostly in strong fields. And the other one is, of course, streaking in single photoionization, where you use a very weak linear polarized streaking field. And I will talk mainly about streaking and the problems, or basically whatever we see there. And in both cases, actually, you will see that non-adiabaticity plays a crucial role. And which role that is, I hope to clarify a little bit in this talk. And you see here, my collaborators are, like always, Ulf Salman, who did most of the work for the streaking part I will present. And Jonathan, as a postdoc, joined us recently from Marseille. And Suomi is working towards her PhD thesis on this topic. So this is just a reminder for you what measuring ultra short time spans in photoionization means. So this is really the Attoclock. And the idea is that, this is already from 2008. One might call this a really important paper by now, of course, from the Ursula Keller group, together with collaborators. The idea is when you set an electron free by basically a strong elliptically polarized laser pulse, then through the same strong pulse, this ionized electron is streaked by the rotating vector potential. So its initial momentum when set free is the vector potential at, let's say, an instant of time tau, which is given essentially by the external rotating laser field. And any difference in the angle between this measured momentum in the end at the detector, vectorial momentum that is, and this initial momentum can be interpreted, of course, as a time delay via the relation of the angular difference of the direction of these two momenta divided by the frequency of the laser pulse. Now, of course, in the beginning, we thought this is wonderful to measure ultra short time spans. By now, we are a bit wiser, almost 10 or more years later. So the electron is set free. I deliberately formulated this very loosely. It's set free at the maximum of the laser amplitude. And the time delay is mostly due to tunneling of the electron, if you measure any, for any times t larger than tau. And the green things are really assumptions which are motivated by the adiabatic tunneling picture. That means by a situation where omega is really very, very small. And there's lots of debate about this, and I think you will debate following our 3 talks even more intensively. And what actually I think has turned out so far, without actually saying what tunneling time is or not, is that certainly the Attoclock electrons are non-adiabatic for 800 nanometer light. And the signature of this non-adiabaticity, I just want to remember you about this or remind you about this, is the energy absorption which occurs under the barrier. I do not say during tunneling through the barrier, deliberately again, I just say under the barrier. And this was our proposal or contribution a couple of years ago. And this was mainly by Hongcheng Ni, who will also be a participant in the battles later on. So I think he will give you more details on that. Therefore, I will be very brief. This can be quantified by so-called classical backpropagation. And in general, the interpretation of timing results, I would say, depend very much on the definition of tunneling. And clearly, tunneling is not a rigorous concept. It's kind of an approximation, since quantum mechanics per se, I would at least claim, does not care about tunneling. It's just quantum mechanics. And tunneling is in a way a semi-classical or even classical concept, which always has its problems. So let's have a quick look on this backpropagation. This is shown here. So we basically solve the tiny bit and Schrödinger equation for normal tunneling or whatever strong field problem. That means we have an helium atom, 1 active electron in its ground state. We solve the tiny bit and Schrödinger equation quantum mechanically in this elliptically, or for us, it's easier in theory, circularly polarized laser field. You see it's a pulse, I think 2 or 4 cycles. And what we do then, once we have propagated for quite some time, we can kind of isolate the ionized fraction far out of the wave packet, far out from the nucleus. And then we convert this basically to a classical probability distribution, and taking this into trajectories by taking the momentum as the gradient of the phase of the wave function of the ionized part, and basically the density for the rest. And then we propagate these trajectories backwards towards the nucleus. So we kind of undo the ionization, if you wish. And now comes your favorite tunneling condition. You can use this to implement any tunneling condition you like. We think the most, how to say, general one is probably to require that at least one momentum component of your tunneling or tunneled wave packet goes through 0 at the tunnel exit. How would you otherwise distinguish that something is tunneling or not? So this is what we do. We kind of stop the wave packet at the closest position where the instant momentum, or the momentum in the instant direction of the laser field, has a 0. And when we do this, we kind of retrieve all the things we discussed before. And you see this here in a quick movie. This was made by Hongcheng for quite a while ago. You see this is circularly polarized laser pulse. A 2-cycle pulse, 800 nanometers, intensity 8 times 10 to the 14th watt per square centimeter. And as I said, helium single active electron. And this is now shown here, the time evolution of the helium density. Going out, it's just the quantum density going back, it's the classical ionized part. Let's see what happens if you see something. So nothing in the beginning, the time is running on top, 0 is the maximum amplitude. Now you see it's going out. Yeah. And this is classical backpropagation. So it's really going nicely back again. And you see in the end it's hollow. Why? Because we took out basically the bound states. So that's only the ionized part coming back. And just to tell you in a nutshell, since I want to emphasize non-adiabaticity, what really happens, you see here in the bottom on the right-hand side, this is the energy we can monitor at this tunnel exit. And you see the energy of the tunnel exit, it's just the average energy of this ionized wave packet. It only agrees with our assumption of adiabatic tunneling. That means nothing changed from the ground state electron, and especially its energy, which is minus 0.9 eV for helium, only for high intensities. Or if you formulate this in terms of a Keldysh parameter, for small Keldysh parameter, or if you wish, in the limit of vanishing frequency. Of course, we varied here the intensity, not the frequency. Varying the frequency is not so easy in theory, and probably also not experiment. So this tells you that non-adiabaticity is an element, a key element in this Attoclock process. And our expectation we have probably, or our intuition, is only met in the adiabatic situation, which is not really achieved in the range of intensities or parameters we kind of use the Attoclock. And of course, we can't use the Attoclock in this limit for very high intensity, because then you have over-barrier ionization, and this doesn't work. So this limit is not reachable for the Attoclock setup, where really adiabaticity is reached. Now you can see this was published, the first publication in 2016 by us. And I think there's another more extensive one in 2018, and Hongcheng has, I think, new interesting stuff he probably will tell you about, Hongcheng Ni. And there's recent reviews about this, just fresh from the press, so to speak, by Anoti Kaifetz, a topical review this year. And last year, Cornelia, who is also a participant in the battles later on, published a review in 2019. And I guess they don't really come to the same conclusion, but that's why it's interesting. So let me continue and come basically to the stuff I really wanted to talk about. This is streaking of single photoionization. Now streaking is again another way to start and stop the clock. So you start the clock by initiate the ionization with an XUV attopulse, and you stop the clock in a way by timing the ionization with IR streaking in the time domain or in the frequency domain with rabbit, with the frequency cone. So the IR field here is very, very weak. It's just really a probe. And the process you want to look at is single photoionization with an XUV pulse and a pulse, because you want to start the clock for photoionization. And of course, the elegant experiment is that both of them are phase locked, because they are generated by the same original strong IR field, the attopulse as well as the streaking pulse. Here are all the papers of the initial kind of ideas and publications. So that's the setup again. You have photoionization, very simple, without any streaking field. That's what we know. Initial state, bound state with a photon frequency omega. That's the central frequency also of the attopulse later, above the threshold, and you end up somewhere in the continuum. And this continuum energy I will call excess energy E in the following, is given by initial energy plus photon energy. Now the streaking idea is that you kind of modulate the energy of the electron where it actually goes to the state in the continuum by a weak streaking pulse here. And that means you put basically a timestamp here on this evolution. So if you come later, you will end up with a different energy in the continuum. That's the whole idea of the streaking. And this gives you then different final electron momenta. You see them here. This is the streaking momentum. It's just basically the interval of the field strength until infinity from the time where it was streaked. And now it can, of course, monitor this and record this as a function of the time delay. And typical parameters in the beginning were 100 EV, XUV photon frequency, 200 attosecond pulse. So this is a streaking spectrogram. And of course, you cannot measure absolute delays in that way, but you can measure elegantly relative delays, because with the same laser pulse, you ionize two different orbitals, let's say in neon, then they have two different excess energies. and you can extract the relative delay for photoelectrons which come from the 2p and the 2s orbital. And this was found in the original experiment to be something like 20 attoseconds. And I think it's still not really reproduced. Maybe it is by now. I have not completely followed the literature. And the question is, that's a clean measurement. What does this delay between these two streaking kind of shifts, what does this really mean? Now, I want to kind of discuss this in the context, of course, of Wigner time delay, because this is the concept theoreticians came up very early with to relate it to. Wigner time delay is an old concept from collision theory. It's related to the scattering matrix here written in the angular momentum basis for conserved angular momenta, which is the case for an electron which comes from a well-defined bound angular momentum and is photonized by a single electron. And then the Wigner time delay is essentially the derivative, the energy derivative of the energy-dependent phase shift. And since photonization is a half collision, you expect half this time delay. So photonization time delay is the energy derivative of the phase of the dipole matrix element. Now, is this really the time determined in the photonization streaking experiments? So this was never really proven. It was shown that it is similar in certain situations, especially for short-range potentials like Yukawa, but it was not really derived from the physical process of a streaked electron momentum. And this is what's measured in the experiment, streaked photoelectron momenta. So what I want to tell you now is an investigation where we really determine the photoelectron momenta directly from energy absorption. And we do this to be transparent in the simplest possible approach, just for proof of principle. That is, we do it classically and we do it in one dimension. Now let's see, first of all, what is the classical Wigner time delay? This is actually very simple. You start propagating your electron trajectory somewhere at the origin in the potential with the final excess energy. So photoionization or absorption has taken place on the final energy surface, now without streaking laser pulse, just pure energy conserving system. And then the time delay is given by the derivative of the action with respect to energy. And that is the relative action of the photoelectron coming out under the action of the potential and the electron coming out without potential. That's the idea of the time delay, the Wigner time delay. You kind of compare the time it takes a particle to come out from a potential compared to a free particle of the same final energy. And of course, now you can calculate this. It takes this form as an integral over r. You see it's the momentum action for those of you who know this, or what's also called the collisional action. And you can convert this, and this is very important, changing the integration variable to a time integral. This brings us closer to the streaking scenario already. And you see P of r is the momentum, including the potential. P sub e is just the free momentum, or also here the asymptotic momentum once the potential is gone. So that's the form. And that means the Wigner time delay is defined so the asymptotic momentum difference of free particle and particle in potential. And here you see the comparison, though this is the Wigner time delay, and this is what we look ahead now for. This is times an attosecond, and this is essentially here the electron excess energy. And you see these are already streaking time shifts, and I will tell you in a second how we calculate them. And this is shown here for a Yukawa potential. And you see already, so it is actually the streaking kind of shifts approach the Wigner time delay, but only in certain limits. So they approach the Wigner time delay if the wavelength is really long, longer and longer, or /and if the electron excess energy is high, but not in general. And this is done here for a Yukawa potential with a screening length of 3 angstrom, just for your reference. So let's see how we can rationalize that. And here's, here's already the first clue. So we write this again in a different form. We write it basically by partial integration as an integral over time, including the potential. And here you see now, this is the derivative of the potential which enters here. And this is kind of an average of time already. So let's come now really to the momentum, the streak momentum, how it can be derived. I should emphasize that all the figures you see are electron momenta calculated numerically without approximation. This is just solution of the full classical equations. But of course, in accordance with the streaking scenario, we are always in a limit where our streaking field, the vector potential of it, over the energy of the photoelectron or its momentum is small, roughly 1%. And what facilitates the understanding, the derivation, is that an analytical expression for the momentum change can be given very easily in a closed form if we assume that the potential is weak. So this is basically the limit in the weak kind of streaking potential, streaking field. Then you see this momentum change is given by this expression or can be written like this. And you probably recognize very easily what is traditionally done in strong field approximation. There is no potential. And then the streaking shift is simply given by the imprint of the vector potential in the beginning where the electron appears in the continuum. But of course, this should be modified through the potential. And that's what we want to calculate. Now I can write this. Now I can parameterize, I would say, my streaking momentum shift simply for harmonic fields in a harmonic basis. This is done here. This is nothing but a reparameterization. And then the streaking shift would be given by the arctant of these two components here. And the nice thing is now, if you parameterize this expression in this way, then you see this component is basically given by that expression involving the derivative of the potential. And you see this is already very close to what we want. But before I come to that, let's see how we read off our streaking kind of time shifts. We simply take the computed, and now this is numerically computed streaked electron momentum, the gray dots here, and fit it to a harmonic, a sinusoidal kind of function, which represents more or less our streaking driving field. And then, of course, we can read off the shift, the time shift, very easily. And you see, for doing this, you need not a special basically delay S to do this. Of course, it gets better if you get through the whole period of the streaking delays, but you can do this at any kind of point S. So without any restriction, we can take S to 0, and then we see the following. So at S equals 0, the streaking shift is given by this expression, and it looks like this one here, quite directly. So it's given basically by chi C because chi S doesn't play a role since its harmonic component is 0 at S equals 0. Now, remember that the Wigner time delay is given by this expression. And now you see where it comes from or where the relation and connection is. So this expression, of course, if omega is small, gives exactly t. Sine omega t over omega gives t. And then you have a direct relation between the streaking shift and the Wigner time delay. So more precisely, in the limit, in the adiabatic limit, you recognize it again, omega to 0, the streaking time shift agrees with the Wigner time delay for a Yukawa potential. This is what we have derived this for. Now you see here a calculation, and miraculously, it also gives you a finite result very nicely, almost similarly for the Coulomb potential. But this is now a contradiction. This should not be, right? Because we know that the Wigner time delay basically does not converge for long range potential. And here's a resolution, at least for the time being. The streaking shift agrees with the Wigner time delay only in the adiabatic limit, omega to 0. And additionally, you need, and this is the adiabaticity condition reformulated because, of course, it's not absolute in omega. It's always relative to another energy scale, that essentially the electron, the photoelectron, should leave the range of the potential in a quarter of a period of the streaking field. So this expression should be much rather larger than RV. And RV is the range of the potential. And this now explains also what I showed you before. Of course, you get kind of good agreement for low, small omega, large wavelengths, but also you get it for high excess energy. This, of course, helps to leave kind of the potential fast. And now comes already kind of where the problem lies for Coulomb. You know, Coulomb has infinite range, so you never really leave the potential. So this adiabaticity condition is never fulfilled for a pure Coulomb problem. And the point is, and we come to this in a second, that the energy absorption kind of really gives you a wrong impression. Of course, what streaking does, it always leads to a finite energy absorption. Since energy is absorbed, you see this here only basically in 1/4 of the streaking period. You see here, this is a strong positive amplitude, strong negative amplitude of the laser field. This is the absorbed energy at different wavelengths. This is for Yukawa, the lower one is for Coulomb. And you see this kind of settles on a certain value roughly after 1/4 of the period. If you change your wavelengths, make it lower, you absorb more. But for Yukawa, this eventually saturates and gives you the limit of the Wigner time delay, what you can extract from this energy absorption. Now for Coulomb, and this is in accordance with the fact that the Coulomb potential has infinite range, this energy absorption never settles. You can make the wavelengths longer and longer. You cut out basically a larger and larger part of the potential where you interact with and still have energy absorption. You get larger and larger energy absorption. So this means that the streaking shifts for the Coulomb potential are finite for the wrong reason, because the streaking terminates energy absorption after 1/4 of the period. And for streaking shifts to resemble a clean system property, which is independent of the properties of your probe field, the streaking field, or the excess energy, the photon electrons really must have left the range of the potential after 1/4 of the streaking period. This is impossible for pure Coulomb. And this is almost the last thing I tell you as an overview, the streaking shifts. So this summarizes what I just said. These are the streaking shifts as a function of wavelengths for a certain excess energy, 10 eV. You see here the Yukawa potential, and you see if you make the wavelengths longer, that's what we discussed, get a very nice limit. And you see here the arrows are really the converged values, which is here for wavelengths of 100 micrometers. So this is really where it's adiabatic, you get a nice converged limit. It agrees with the Wigner time delay. Now for Coulomb, you see this increases, the streaking shifts, they increase and increase. There's no chance for get convergence. Now, if you do the same thing now for basically 2 different energies, you see the dilemma that even that doesn't help, because absolutely speaking, the streaking shift for Coulomb potential really depends also on the excess energy. So at 10 eV, you get this excess energy, at 30, you get this one. The difference gives you the black line. Also, this one doesn't converge. So it gives you, of course, a finite value, but it's not necessarily what you should associate with a clean system property. The only way to achieve this is basically if you kind of gauge your Coulombic potential, which has a Coulomb tail. That's a realistic thing. You never have pure Coulomb systems, only hydrogen is that. If you kind of reference your Coulombic tail, instead of the free particle, as it is for the Wigner time delay, with the Coulomb particle, that is a pure Coulomb potential. That's a reference here. If you do this in the same spirit as for the Wigner time delay, take the difference in the momenta, then you actually get a converged value. And this is what we would probably propose. And you see here, the Coulomb potential is, the Coulombic one is just mimicked as a soft core with a finite soft core parameter of 3 angstrom here. So the streaking shift for potential with Coulomb tail must be referenced with pure Coulomb potential shift for adiabatic convergence. Then you get a limit which is independent basically of your properties of the probing pulse. And that's very important, comparing shifts of 2 orbitals. What was done originally, and this seems to be very elegant, of course, in the experiment, with the same laser does not help, because this is exactly this situation. You have different excess energies, and that also does not converge. So that's a summary. Adiabaticity is the key condition which ultrafast timing techniques need to do what they should do. And non-adiabaticity is very interesting for theoreticians, but it's not really very helpful if you want to use this as a passive technique for bringing out properties of your target system. And in particular for streaking and photoionization, adiabaticity lets streaking shifts converge to Wigner delay for short range potentials. And streaking shifts for Coulomb potentials are finite for the wrong reason. They should be measured relative to reference system, Coulomb reference system, at the same excess energy. And as I said, in the end, traditional relative streaking shifts of two ionized orbitals with a different binding energy with the same light path, this does not really help because they have different excess energy. So I'm done. Thanks for your attention.
So yeah, Michelle, thanks for the nice talk. Are there questions, comments? Please type the questions in the QA box for those who are attending. And the first question is from Heiner Donna. Can you comment on timing of multiphoton transitions?
We have not done this explicitly, but of course, multiphoton transitions are in general in the very kind of, how to say, non-adiabatic limit, if you think of the Keldysh parameter. So I would expect they're really a different kind of physics.
Thanks a lot. I also have one question because I was seeing that you were defining adiabaticity, and some people would say that you not necessarily have to have a constant energy, but you have to have some energy that is gradually changing and adapting to your external conditions. I know this is a question of definition, and we are talking here about metals, so many people would agree on some concept and some people would disagree on the concept. But if you look at the definition, for instance, by Born and Fock, what they say is that you can, for an adiabatic system, define an instantaneous eigenstate that should change. So naively speaking, if you think about it, for instance, you have an effective potential that is changing over time, which is composed by the field and whatever barrier you have. Could you not say this is adiabatic?
So I think you're right. In general, adiabaticity, what adiabaticity is concerned, I mean, in the context of time shifts and streaking, it's very clear, I think, and I make clear what adiabaticity I have in mind. So what I think we need is that our measuring apparatus does not kind of change the thing we want to measure. Otherwise, it's not what we normally call a measurement. We can still do this, and of course, all the measurements are correct, but the interpretation normally relies on this assumed concept of adiabatic change, or something has not really changed in terms of properties of the target. And I tried to convey that this is for standard setups of basically our ultra short timing concepts, Attoclock as well as streaking. This is not necessarily given. So in the streaking context, this is actually mostly fulfilled for 800 nanometers and for the target systems we use. Yet you see, it's very tricky because, as you say, it's not absolute with the frequency. It's always relative. I mean, it needs to be small compared to another energy, right? That's the excess energy of the electron. That's kind of the internal time scale of your potential, the asymptotic excess energy of the photoelectron. And also, and this is kind of surprising, that basically the timing, the streaking time shift really depends on this excess energy. Therefore, this kind of natural and not naive, it's, I think, very clever of comparing two orbitals, right, being ionized by the same laser does not help. This does not give a converged value which is independent of your properties of the streaking field. So therefore, one needs really to think how adiabaticity figures in which aspect.
Yeah, thank you. I think it's a key question because a lot of people, they talk about adiabaticity and you see that the concept is oversimplified many times. And I think this is a key issue. We also have here a question from Hanjit. And they're asking, could you please tell me which method are you using for wave packet propagation?
So we use here purely classical wave packet propagation because it's photoionization, we are high above the threshold. And so there's nothing to worry about tunneling or something like this. And yeah, it's classical, basically molecular dynamics, if you wish. And it's actually sufficient to extract the timing, sufficient to take the lead or the characteristic trajectory, which is the maximum of your Gaussian or whatever distribution of a wave packet. So taking the full wave packet, you can do this. We also did this. This only kind of reduces the contrast in your signals you measure, but it gives you the same result.
Thank you. Andrew Brown would like also to talk about this question. So Andrew, you wanted to refer to the previous question. Can you please unmute yourself?
I don't have another question, just there are several questions still in the Q&A to be answered there.
Yes, okay. So from Camilo Ruiz Mendes, he would like to know what about measuring stereo Wigner time delays, which means using the same final excess energy. Is that better than using two orbitals?
Yeah, I mean, measuring the same final excess energy is definitely okay. This is what comes out from this analysis. So that makes a valid reference in a way, yeah.
So Jens Biegert would also like to know, when going to ever longer wavelengths, the magnetic field component gets more prominent. How about that component for the timing momentum changes? Yeah, we know this is a real issue, so we would like to know.
Very good question. We will tackle this in the future.
Okay, very good. So now we have a raised hand. Let me have a look.
And I could just answer one more question, which comes as next in the chat. Of course, we are working right now on Rabbit. This will be the quantum version in general, and this should also then, of course, we expect the same kind of conclusion to apply also to the Rabbit technique of streaking. And we're working on this, and this is, of course, the quantum version, which needs interference.
Okay, so there is a raised hand. Henry, you are hosting. Can you allow the raised hand, please, to speak? Where is it?
I'm trying to find who it is who's raised their hand.
Yeah, because we have a lot of people and we have one raised hand.
What's the participant's name?
I don't know, someone raised the hand. So I think we're okay with the questions in the QA box, but there was one raised hand and
so while you are trying to find the raised hand, I can try to answer the next question in the box, which says, how does the adiabaticity play a role in non-Coulombic, non-spherical potential, where an angle plays a role in the photoionization? And this would not matter. I think this can be done in the very same way, because you can essentially formulate everything not in terms of partial waves for conserved angular momentum, time delay, but just basically as a vector and then scalar product for the time delay of the PDR, the action. So the action is a scalar, and it doesn't matter if the angular momentum is conserved or not, and this is all you need.
okay, I think we can continue this discussion on Slack. For those who have not yet registered for Slack, we have channels related to each section. So if you have further questions, you can go there and ask the speaker directly, and we can continue the debate. We're going to move now to our next speaker, and is Robert Moshammer. And he's going to talk about what is time in photoionization in strong and weak fields.
Okay, can you hear me? I hope so. If not, let me know. Hello to the crowd. And thanks, a lot of thanks to Carla, Andrew, and her team for organizing this. Actually, it's my first big conference since quite some time. Let me try to start this screen here and start the talk. I hope you see it. You see also already from my first slide, I'm still used to kind of old style Beamer talks with big letters and not that many text on the transparencies, but maybe it's also helpful now. So let me start. This is my, I cannot switch now. Here. This is the outline of my talk. I will also talk a little bit about methods, which already Jan-Michael did quite very well, so I can go quick here. But let me give some remarks on different methods. I will present a data and an experiment that is already quite some years ago, but it fits perfectly to the subject of this session here: tunneling time of an atom, a measurement and theory, and then some very new results on ionization of hydrogen, molecular hydrogen, rapid measurements where we look at sidebands and time delays. This is very fresh and still kind of under discussion from our side. Okay, so here are the methods. There are basically, Jan-Michael already mentioned this, 3 or 2 well-established methods. One is the Attoclock and one is electron streaking that we heard about, and rapid. And streaking and rapid are very similar. In streaking, you use a single attosecond pulse and you streak with an IR pulse. In rapid, you use a sequence of attosecond pulses. And eventually, you get very similar equations here for the time shifts that you are aiming to measure. This is this factor A here, this tau A, and this is a sum of 2 contributions. It's the atomic or the pure Wigner time that we heard about. And there's an additional shift. This is coming due to the interaction of the electron with the laser in the continuum, or with the IR photons, dipole transitions in the continuum. But for both cases, this phase here is exactly is actually the same. So the method is very similar. And what you do usually, these are the famous experiments here for the neon measurements, either in streaking or with rapid, you measure shifts of traces, of electron traces for 2 different states that get ionized. So you have 2 different lines in the continuum, 2 different energies, and you analyze this this tiny delay here, this tiny shift in terms of delay. And here are my remarks. And from those, you already can see that I'm not that convinced about these concepts at all, but it's kind of useful to learn something, because what we all rely on is kind of a single particle or an active electron picture. Just one electron is active. We don't treat the system as a whole. And sometimes this can be very problematic. It causes kind of misunderstandings, and it also changes the values that you measure. I agree that very often you can correct for this with a good theory, but what eventually would be needed to solve this problem as a whole. It's also assumed, and this was also discussed in the last talk, that we always assume that the IR streaking field is weak. So changes of the molecular or atomic structure due to the streaking field is neglected. This is also kind of a problematic issue, because good results you get only in the limit of a vanishing streaking field. And what we measure in the experiments is time shifts or phase shifts. And from this we extract Wigner times, or in other words, shapes of binding potentials. This was also now nicely discussed by Jan-Michael. So we measure the shape of a potential. And this is getting problematic if we talk about long range or Coulombic potentials. And very similar, these concepts are then, for example, to other measurements where you measure, for example, simply cross-sections of some processes. There's another method to measure times, and this is the Attoclock concept, also presented by Jan-Michael, where we just measure a shift of the momentum distribution of the emitted electron in the plane of the polarization of the laser with a elliptically polarized light. And then we interpret this shift, this tilt in angle as a time delay. And the same holds also true here. The results and the interpretation depend on the physical model, on the mechanism. So we always rely on a mechanism. This, I agree, is the fun part because it leads to a lot of discussions. And this is what also brings us further in our understanding. But it's also a little bit kind of dangerous because at the end, I think you don't even need to have to use this tunneling concept in the case of a strong field. You could also describe it in terms of a multi-photon transition. So the measurement relies also on a single particle picture, one active electron. Very often we have problems or neglect even other processes, other interactions. It might work for atomic hydrogen. There will be a talk by Klaus Bartschat, I think tomorrow. And it is also sensitive to the laser parameters, also to macroscopic parameters. If we do not measure time directly, we infer the time from a momentum measurement. Okay, let me come to my first kind of results, tunnel ionization of an atom. This is an experiment that we did already some years ago. And we looked for the elliptical polarized light, tunneling of an electron through the barrier. And we asked now, not about the time directly, but how good is theory? Can we understand with theory, with the model, the results that we get? We use a simple picture that we treat the tunneling process here out of through this barrier here, quantum mechanically, and afterwards the electron is treated as moving like a classical particle in the electric field of the laser, including the interaction with the remaining ion. And you know that there's a kind of a huge debate since many years, which is the fun part, I think. What is this time? Is there a time? Some experiments say there is some time. Some theories say there is a zero time. Some of them predict a time, so it depends. And why is it so difficult? Because time is not really an observable in quantum mechanics. We have no time operator, so it's hard to define even a time. And similarly, we cannot really define a starting and an end point of a trajectory in quantum mechanics. But this is needed in order to extract the time. And there are many options here to really kind of characterize or define the trajectory of a quantum particle. But this depends then also on the interpretation and the picture that we are using. So in this context, if we now discuss tunneling, we need somehow a definition of time. What do we mean with time? And we use here a very simple concept. We say, okay, we use quantum mechanics to describe the tunneling out of the barrier here. And afterwards, we use classical mechanics, a classical trajectory to describe the motion of the electron in the presence of the field and the remaining ion. So in order to start to launch this classical trajectory, we have to define initial parameters. And the initial parameters should be the initial momentum and the time after the maximum of the laser field at which we should start this trajectory. So once we have these parameters, the time and the initial momentum, then we can launch our classical trajectory, and we should get a very good agreement with experiment if everything is well described. Okay, in the experiment, we are looking to the electron momentum distribution, as I said. So if, for example, your laser electric field is polarized like here on the upper picture, elliptically elongated along the y-axis, you will measure electron momenta along the x direction. This is just because of the motion in the electric field of the laser. And you should see maxima along the px axis, and these maxima are now tilted out of the px axis, first because of Coulomb interaction of the electron with its own ion. This already leads to a kind of a tilt here, but this is just purely Coulomb interaction. There's nothing to do with the time or any tunneling time or anything else. This is one effect, a big effect. And we measure this in our lab by using a kind of a Coltrane's reaction microscope. So we send in a laser with circularly polarized light, long wavelengths in order to avoid some of the problems of non-adiabaticity, long wavelengths and intensities in the range of 10 to the 14, as low as possible. And we use in the experiment, and this is the trick now, a mixture of argon and krypton, two different gases. And we measure them simultaneously. So we get electron spectra for both targets in absolutely identical conditions measured at the same time. And we analyze now from this experiment, just the differences between these two spectra, between argon and kryptons for different intensities of our laser. So what we do, these are the two targets with slightly different ionization potentials. Consider just one active electron. The electron is moving in a kind of a Hartree-Fock type potential that is deformed by the laser field. In the theory, then we solve the Schrödinger equation of the electron in this static field. And from this solution, then we get the initial parameters for our classical trajectories. So these are the experimental results for one specific laser intensity for argon and for krypton. And you see these spectra are again now tilted along with respect to the x-axis, and they look very similar. Actually, if you compare and have now a somewhat closer look, you see they are different. The difference is tiny. This is the difference of both spectra. It's in the order of 10 to the -4. So there is a small difference. And now we're going to analyze this difference. So we look to the quantities here, the ionization yield, the average radius of this momentum distribution, and the tilt angle. And for example, the total ionization yield, we plot the ratio of argon and krypton here as a function of the momentum of argon electrons, and because the momentum scales with the intensity. And if we do everything correct in our calculation, so we have to consider depletion, we have to consider focal volume averaging, the influence of the Coulomb interaction with the electron with the ion, all this has to go in. It's not that tricky, but then at the end of the day, you get a curve from theory, which fits very well with our experiment, if the parameters are all fixed. We can also look to the average radius of this distribution here. And we get also a very good agreement here with theory if we use a starting momentum from theory now either not equal to 0 or equal to 0 at the exit of the tunnel, if you want. And there's a slight difference here between two equations, two formulas, where one is the non-adiabaticity is included, or an effect of non-adiabaticity is such that during the tunneling, the direction of the laser field changes a little bit, and this is included in this solid line here. And again, we see a very good agreement with experiment. And here is plotted the tilt angle from the distribution here. And again, the differences between the two targets. If we use the standard simple man model, just tunneling, starting a classical trajectories at the exit of the tunnel, with 0 initial momentum and with 0 time, then we get this dashed line. If we use our theory, the quantum theory, for the initial values, there is a certain start initial momentum, there is a time for kind of tunneling, if you want, then we get this solid curve here, so a much better agreement. And this shows the result of these different trajectories, these different calculations. What is plotted here are trajectories, so x versus t or t versus x. The yellow line here is, so to say, our simple man picture, where at the exit of the tunnel, which is well defined in a simple man picture, we launch our electron with 0 velocity at the position of the exit, and you get then this trajectory here, the yellow one. If we use, for example, the solution of our quantum calculation and now define a trajectory in terms of a Wigner trajectory, same concept as you have heard. So we define a trajectory by just taking the derivative of the phase of our quantum solution with respect to the energy. Then we get this dashed curve here. In principle, we can extend this dashed curve to long distances, but we decided now that we want to match this dashed quantum solution with a classical solution or the classical propagation right at the classical exit point, and then propagate the particle with the initial parameters that we get from our quantum calculation. And if we do this, then we can extract the tunneling time, if you want, the time that we should plug in as a starting parameter for our classical trajectories as a function of the intensity, and the initial momentum, which we should put into our equation for the classical trajectory at the classical exit point of the tunnel. And if we do all this, and this was really amazing, this was kind of a real aha effect for me, we get a very, very good agreement, this experiment, so almost a perfect agreement. So if we include the values for the tunneling time, if you want, and the initial momentum into a classical propagation, a classical model, then we get perfect agreement with experiment. As I said, this was a kind of surprising for me, but I leave it to you now to interpret these times as being a tunneling time or not, but this is a very well-defined concept, and it describes experiment very well. Let me come to my second subject, and this is rapid now. It's a rapid experiment. And during the last 2 years, we set up a high harmonic beamline in our lab. Here's a sketch of this beamline. So the laser is coming in, high harmonic source, and a reaction microscope. So we drive this thing with a fiber laser, 1,000 nanometers, up to 150 kilohertz. Power is going up to 150 watt. We drive our high harmonic source. It was a little bit tricky to get it running. Here's a more detailed view of our gas nozzle. Actually, these are 10 gas nozzles in a row. And you see the plasma that we ignite with about 150 watt here and produce harmonics. And these harmonics we sent into our reaction microscope and do experiments now, kind of rapid type experiments. So this is a sketch of the XUV photons that we get. And if we do an experiment just with an atom, let's say argon in this case, then this is the photoelectrons that we get just using the harmonics. And you know that we now, if we also superimpose the IR field, then we get the so-called sidebands here. And we produce sidebands that now are sensitive to the time delay between the XUV pulses and the IR pulses. And here is a streaking trace of those electrons here as a function of the delay. You see the period is 1.7 femtoseconds, 1,000 nanometer laser. And again, now we can look for time shifts by looking at these phases here. Same concept holds. The phase shift is determined by the Wigner time and Coulomb-Coulomb coupling time. Okay, now let's do this with H2. A little bit more complicated. And I want to show you an experiment which is actually very similar to a recent experiment by the Zurich group, by Laura Cattaneo, published 2 years ago. They also measured rapid traces for H2. I will come back to this in a few minutes. So and these are the data that we get for H2. So we produce a lot of singly charged molecular ions and fragments, H+. And if we look now to the electron spectra, this is already the superposition of XUV plus IR. So there should be a lot of sidebands. This is the electron spectrum here in the lower part. And you see everything is very much broadened. So it's hard to resolve even the sidebands. In some cases here, you don't even see them. So it's very fuzzy. There's a good reason for this, because we ionize our H2 and end up in an H2 plus in the ground state, in the electronic ground state, but with a lot of vibrational excitation. This vibrational excitation can lead to a broadening in the order of 2 eV. That's just the distance between the harmonics here. So this broadening smears out everything. So what to do? There's a much easier concept. Let's look for another channel, for a more well-defined channel from the kinematic side. So we look for ionization plus dissociation. So we go from the ground state of H2 to a dissociating state here. And what is most likely happens that we go to the doubly excited state, a dissociating state, and then the total energy, the sum energy of the emitted electron and the kinetic energy of the ions is fixed, is given by the XUV energy. So if you plot this energy partitioning here, you see sharp lines, and these are just the harmonics. Here we use XUV only. And the main channel in this spectrum here is coming from doubly excited Q states, where we excite 2 electrons at once. This state decays via autoionization. So an electron is emitted and the ions get some kinetic energy, and this is what is plotted here. Okay, so far so good. So now let's have a little bit closer look here and look to lower kinetic energies, because there the same concept works. You can also just ionize to the ground state of the molecular ion, and still get dissociation. Then you get lower kinetic energies of ions and well-resolved electron energies. But this is still without IR. Now let's switch on the IR for doing rapid or streaking. Then we see an additional lines here. These are the sideband lines. And you see a blob here at about 0.6 eV kinetic energy for the ions. And if you go, for example, on one of those sidebands here up, you see at some point, this, what was before a sideband, is now getting more prominent compared to the harmonics. So what's happening here is that that one electron is emitted by the XUV, and the remaining electron in the H2 plus is excited to the ungerade state. Then we get dissociation, and these are these sharp blobs here. Okay, let's go further. And now let's look to the phases there here. And let's look, for example, for a selected kinetic energy window. We choose this part here, where we know that we have a contribution coming from these doubly excited Q states and direct ionization. And we also know that if we choose, for example, the ions preferentially emitted along the laser polarization, then we preferably have events coming from the doubly excited states. If we look perpendicular to the laser polarization, then the direct dissociation is a little bit more dominant. So we select a kinetic energy window for the ions here, and then look for the sidebands. And we look for the phases tau A here. And a closer analysis now shows us that these phases tau A, or shifts, are already converted, these shifts here, in time. So we see for parallel orientation, there is some chunk going on here, some jump, a kind of characteristic structure where the perpendicular phases are more or less straight, smooth. And what is this? So this is appeared not just in one experiment, and actually what I'm showing here are data for D2, not H2, but D2. The reason I will explain in a second. So what happens here is exactly at these 29 eV or 30 eV here, we reach these Q states. So we excite the doubly excited states. The system rolls down here, and after some time, an electron is emitted via Auger ionization. So the question would be, has this time delay here between excitation and decay, is this somehow reflected in this yellow curve here? So what we did, we calculated just a classical propagation of the nuclear wave packet here along the Q states, and looked what kind of kinetic energy we get, kinetic energy for the ions as a function of the lifetime of these doubly excited states. And then you see for the kinetic energy window that we took between 0.1 and 0.4 eV, or let's take 0.2, a time of about 0.5 femtoseconds, 500 attoseconds for D2. If you do the same experiment for H2, this time is smaller. It's on the order of square root of 2 smaller, roughly. Sorry. So the interpretation now is that this jump here in the phase might be related to the lifetime of the doubly excited states here that we select with our kinetic energy release window. And now the problem is, in order to get a kind of an oscillation of the sidebands, we have to define somehow the interfering rapid pathways. This is not that easy here with a single electron that is emitted in a single ionization. It's definitely easier because you could imagine that we excite this doubly excited state via these two different paths here, coming directly from below or going first up and then re-emit an IR photon. But then the question would be, why do we then see a shift in time or in the phase? Or there are other possibilities that these IR photons interact during the decay, during the auto-ionization of the electron. In the moment, we simply don't know. And let me also compare this with the data from the Zurich group. They did very similar data for a much, much larger kinetic energy release range. So we should roughly compare the blue curve here with our yellow curve. You see that qualitatively there is agreement. Quantitatively, there is a difference, a big difference, because we measure much, much larger times here, about 0.5 femtoseconds, and they are in the range of 100 attoseconds. Interestingly, in their paper, they also had a theory calculation from Fernando Martin, and they even predicted also the similar shape, but the values are even lower by a further factor of 10. So you see, it's kind of a little bit tricky to interpret this data here. So we see sideband oscillations also in H2. The straightforward interpretation is getting much more difficult. It's not like in the single ionization of an atom. We expect, or we think, that these sideband phases are sensitive to the lifetimes, for example, for the doubly excited states. But eventually we need a theory to really get a quantitative understanding. Okay, I think I'm already a little bit over time, and with this I want to stop here, but I don't want to stop it without mentioning all the people that did the work. So in particular, the crew on the experiment. So this is Nicolas Camus from for the tunneling experiment, Farshad, Hem, Divya, and Anne for the high harmonics experiment, and we had help also for the tunneling case from theory from our institute here in Heidelberg. And with this, I want to thank you for your attention, and I will be happy to answer some of your questions. Thank you.
So thank you very much for your nice talk. Are there questions, comments? Just a remark, if your questions from the previous talk have not been answered, we would appreciate if you could post them on our Slack channel. They are sometimes arriving with a delay. So is there any question related to Robert's talk? I don't see any so far, but I have one, and this is related because you showed this picture from the theory developed by the Keitel group, and you showed that if you calculate a Wigner trajectory, works pretty well with regard to the experiments. Now, my question is, did they have to go to the complex plane? Did they not? Did they use a Wigner quasi-probability distribution? How did they compute that? Because we know that to calculate these things can be really hard, and sometimes you have to make approximations which can compromise your theory.
This is now a little bit hard for me to answer in detail as far as I understood it. So they solve the Schrödinger equation, the time independent Schrödinger equation for a static field, the binding potential plus the external laser field. This is a complex wave function, I'm sure. And from this wave function, they extract the Wigner trajectory, which they at least can provide, or also for motion under the tunnel, if you want, in quotation marks. But how they do it in detail, I simply cannot answer. So what is considered in the calculation, what is taken care of is the kind of the multi-electron effects are included such that they use kind of a Hartley-Fock potential. What is also included is polarization of after the electron has been emitted of the remaining ion. So there are a few kind of tricks included in the calculation, but details I'm over asked now.
Yeah, okay, fair enough. Thank you. Sergey, would you like to ask something? I can see you.
No, I just logged in, sorry.
No worries. Would you like to ask something? Okay, we have one in our Q&A, and this is from Jing Cheng. Can you fit the difference between argon and crypto in Attoclock measurement by only considering the initial longitudinal momentum without tunneling delay?
No. You get this. What fit means one gets an agreement with it is as good as it is now, with including the longitudinal momentum, the tunneling time. No, the agreement gets worse. This is not a huge effect, but it gets worse. So the best condition you get if you include the initial longitudinal momentum plus the tunneling time delay, if you want.
Are there any further questions? I cannot see any. They sometimes, there's one. Takes a time delay also for the questions, you know. So from Jens Bigard, I assume if 2 species rabbit use low gas pressures, would it be interesting, crazy to try a high pressure so that the ionic species influence each other differently? See old paper from Andreas Becker.
It is a low gas pressure. Yeah, I think I assume Jens is talking about the tunneling experiment with the krypton and argon. So this is definitely a kind of very dilute target. So individual atoms. I have no idea what happens if you use really a high pressure target. But because the trick here is also to kind of sign the emitted electron to its respective ion. So we need kind of do kind of coincidence measurement to label the electrons. If this would be possible with high density, I don't know. But maybe I simply misunderstood the question now.
Okay, can you clarify? Jens, can you type another one? If not, we should keep on moving. Please don't forget, if you would like to ask further questions, to type your questions on our Slack channel. We have one channel for each sections. And let's thank Robert again for his talk. So thank you so much. And moving on, now the last talk of the session is by Lars Madsen from Aarhus, and he's going to talk about tunneling theory of molecules.
Yeah, so I think I need someone allowing my video. Yeah, okay. And yeah, so hello everyone. Let me start by thanking the organizers for setting up this new meeting format in these times. And it's not just a regular meeting, it's much more with interaction possibilities on Slack and whatnot. So for me, at least, this has been kind of an eye-opening experience in terms of new ways we can communicate as a scientific community, communicate scientifically. So I think this is great. So let me start sharing the screen, and I will start my PowerPoint presentation. I changed the title a little bit. As you can see, it's a longer title now. And before I start, I'd also like to say that I put more text on these slides than I normally do, because I was a little bit thinking about the format, that maybe it was nice to have more stuff to read, and you'll also be able to go back and have a look on the slides using YouTube and other things. So the title is Multi-Electron Polarization and Non-Dipole Effects in Strong Field Ionization. And the motivation for this talk and for the work that I'll present is listed here. And it's very much related to some of the things we've already heard in the previous talks, namely that we face a number of fundamental and computational challenges. For example, we actually have difficulties dealing with more than 2 electrons if we want to try to pursue any problem using ab initio techniques. So what to do if we have more than 2 electrons? And in addition, there are a number of approximations that enter our fundamental description in the laser-matter interaction, such as the electric dipole, for example, which we tend to do, but we are not always sure that this is okay. So these kind of thoughts led me to the following 2 questions, namely how to deal with the time-dependent non-perturbative driving of a multi-electron system, and how to deal with situation where the nature of the external laser pulses leads to a breakdown of a conventional approximation like the electric dipole approximation. And in this talk, I'll address certain aspects of these 2 points. Let's see. So specifically, I will give a status on the formulation and numerical implementation of a tunneling theory for large molecules with many electrons. And after that, I'll show how multi-electron polarization effects may lead to a simplification of a response of a many electron system, which in fact can lead to an accurate formulation of a single active electron model. And in the end, I'll show how to include in an approximate but accurate manner non-dipole effects in strong field ionization and strong field light matter interaction scenarios. So this is the 3 topics, and topic 1 is tunneling theory as promised, and I list here in this slide the papers on which this part of the talk is based, and you can look up those references and also other relevant papers there. So if the timescale of the variation of the external field is sufficiently low, we are led to this tunneling picture as shown in this view graph, where the external fields distorts the atomic or molecular potential and the bound state can leak out. And now if we have this situation, we then study this for a fixed field strength. So this is a tunneling problem. So now I simply assume that this assumption of this adiabatic approach is fulfilled, and we focus on that one. As you see here from the figure, traditionally what we have done is that we have looked at this problem by doing some matching out here in this asymptotic region. So most tunneling theories are formulated in the so-called, what I would call tail representation, where you are occupied by the behavior of the tail of the bound state wave function matching to an outgoing wave. And this was also the way we formulated the original theory here, the weak field asymptotic theory, which was describing the situation of tunneling ionization from polar molecules. And I collect some formulas here on this slide. What you have here is basically the things that one needs to calculate for determining the tunneling rate of any molecule. And up here on the top, you have the ionization rate with some so-called parabolic quantum numbers reflecting that the problem of Coulomb potential plus external static field separates in parabolic coordinates. And the rate includes a structure factor and a field factor. And the field factor is the one that you find in most works on tunneling, namely this exponential one, which has a characteristic dependence on the binding energy E0 and the field strength F. And then there's some free factors here also reflecting the parabolic quantum numbers. And then, so this, whereas this is pretty standard for any system, and it doesn't reflect much properties of the system except the binding energy, this structure factor is more interesting because it includes information about the dipole of the ionizing orbital, and it also includes this thing which we call the asymptotic coefficient, which has information about the ionizing orbital in some large eta limit, meaning at large distances. So here you have something which is a property of the ionizing orbital, and therefore this is a system-specific property. And this is somehow the difficult thing to calculate, because you need information about the orbital at large distances. So, and there's a problem with this, because if you want to go to large systems, large molecules, eventually you will have to go to kind of standard quantum chemistry methods or quantum chemistry software. And they're all, or at least the typical approaches are based on expanding the orbitals in Gaussian type orbitals, which fall off too quickly to have a good representation of the tail. So, this is a problem, and therefore it would be advantageous if we could evaluate tunneling theory in a different way, namely in a way that relied on description of the wave function closer to the nucleus, where the Gaussian type orbitals have weight and where the representation of the wave function is accurate. And it is indeed possible to formulate tunneling theory in this manner using an integral representation. So this is what is discussed in this slide. And as I say, it's possible to obtain the tunneling rate from an integral, meaning a matrix element. And if you think on what we know from scattering theory, this may seem natural, since we know from scattering theory that scattering information can be obtained both from kind of a tail property through phase shifts, or alternatively from the T-matrix element, which is the integral approach. Anyways, we can obtain this asymptotic coefficient in terms of an integral written symbolically here, and these functions are confluent hybrid geometric functions and a core potential. And the point is that now this type of approach picks, of course, contributions up to the integral where these Gaussian type orbitals representing the ionizing orbital have weight. And you can find the formulation in the papers listed here. So there's a new way of formulating tunneling. Instead of looking at the asymptotic form of the wave function, you can look at this integral formulation. And this one we have implemented. And it's possible to go to very big systems. And for someone like me who started out in atomic physics, bifinal is a big system. And here's an example illustrating what we can do. So in this particular case, we have the field pointing in the positive Z direction, and we have bifinal, which consists of two benzene rings. And what we calculated here was the ionization rates, these gammas, as function of the angle between the two benzene planes. This is called the dihedral angle. And we can also calculate the structure factor, which is needed. And the conclusion is that the structure factor can now be evaluated with this integral formulation. And this allows a determination of the tunneling ionization rate for any system where the wave function can be determined by quantum chemistry methods. And this is important because tunneling is still used as an initial key step in much of strong field physics. So this concludes the first part of the talk, and leads me to the second one, namely on multi-electron polarization. And some aspects of this multi-electron polarization were already alluded to in Robert's talk when he discussed the modeling of the argon and krypton experiments, namely this with the polarization. And this is what we will discuss now. So as I see it in strong field single ionization of a many electron system, multi-electron polarization has two dominant effects. First of all, we have, if we look at the effective potential of an outgoing electron, it will feel the interaction with the laser, it will feel the Coulomb potential, and it will then, to the next leading order, it will feel an induced dipole potential and a permanent dipole potential if the system has a permanent dipole. And this induced dipole potential here is expressed in terms of the polarizability and the field, and therefore this of course has something to do with the polarization of the system. The other effect, which is also very interesting and in fact helpful for us, surprisingly, is that there is a turning off effect of the laser-electron interaction at small distances. The way to understand this is as follows. The electric field associated with the polarization of the core electrons counteracts the external field and leads to a cancellation of the laser-electron interaction. And it's simply because there's a rearrangement of the core electrons until they feel no effective field. So a rearrangement that sets up a field at short distances inside the atomic or molecular system that has a direction opposite to the external field, but with the same magnitude. So these kind of considerations lead us to thinking about different types of potentials, as indicated here in this view graph here to the left, where I have a field-free potential. This is the blue curve. I have an instantaneous distorted potential. This is the dashed red one. And then I have the crosses, which describe the field-induced potential, where we have the polarization effect included. So the effect of the field is switched off at small distances, and here at large distances we have the induced dipole potential. And we then tried another one where we just said, well, maybe this switching off here at large at small distances is the most important, and then we just kill the polarization effect in the outer region. So these are the kind of potentials that we're led to, and we wanted to have a look how these different types of potential, single active electron potential, capturing multi-electron polarization effects, perform in actual calculations and perform when compared with experimental data. And for that reason, we took our time-dependent Schrödinger equation solver, and in the so-called length scales formulation, where the interaction with the external field can be expressed like this: E times R times cosine theta, or in terms of suitably normalized Legendre polynomials, we can easily include the type of potentials I just presented to you. So we have the same interaction as before, and we can include the multi-electron polarization beyond the cutoff radius, like this, and below we just have the screening effect, and we can also just include some scaling function here that turns off the interaction beyond the cutoff radius. So these are the models that we are going to use and look at. And as an example of the behavior of this type of approach, we consider the orientation-dependent ionization from the highest occupied molecular orbital in the CO molecule. And this is now as function of orientation angle. And so on the x-axis, you have the angle between the CO axis and the dominant half cycle of a 2-cycle pulse at 800 nanometer and at an intensity of 8.8 times 10 to the 13 watts per square centimeter. And then you have the total yield on the y-axis. In the figure to the left, there is no polarization effect included, and in the figure to the right, there is polarization effects included. Okay, now it's interesting to note that the results to the right qualitatively agrees with the experimental results, and this agreement, together with the completely opposite trend when multi-electron polarization effects are not included, illustrates the importance of accounting for these multi-electron polarization effects. And we can also look at the model where we simply turn off the polarization potential beyond the cutoff radius, and that's the difference between the crosses and the circles. And for a system like CO, it's actually fairly accurate just to switch off the potential beyond the cutoff radius. The screening in the inner region is the main physical effect, it seems. We can also look at momentum distributions, in this case, You have the laser polarization in the Z direction here, and here you have frames showing the momentum distribution. And we see that these momentum distributions are not very sensitive to the polarization-induced dipole term as seen from the agreement between the results to the left, which include full multi-electron polarization, and the results to the right, which simply turn off the multi-electron polarization beyond the cutoff radius. And therefore, you could say that it seems that multi-electron polarization effects can be easily and accurately accounted for by the method described here. And it also seems that some types of observables are maybe not very sensitive to the exact form of the outer part of the laser-induced dipole term. The main physics seems to be captured by the screening at smaller distances. Very good. This brings me to the already to the last topic on non-dipole effects. And this part of the talk is based on recent work published this year. So you can have a look. I think this, now having listened to the other talks, I think this topic here is central. It's also related to one of the questions on magnetic effects in the adiabatic regime, because when we have more and more laser sources available at long wavelengths, we will have a relative higher effect of the magnetic component, of the Lorentz force component, and it could be that it's difficult to really consider the omega going to zero limit in laser matter interaction without taking into consideration non-dipole effects. So let's start. So traditionally, the dipole approximation is introduced, and in the dipole approximation, we approximate the spatial part of the electromagnetic field, written here, where KL is the wave vector of the propagating light and R is the position of the electron, by unity. Right? So naturally, this approximation assumes that the laser varies very little over the extent of the atom or molecule. Basically, this one here is assumed. So that's what we normally do. On the other hand, it has been known for many years, of course, that if this condition is no longer fulfilled, you will have a breakdown of the dipole approximation. We saw that many years ago if omega becomes big. So in somehow the opposite regime of what is relevant when you talk about tunneling, it has been known that the dipole approximation breaks down. And it has also been known that a typical signature of the breakdown is a lack of forward-backward symmetry with respect to the laser propagation direction. More recently, in strong field physics at mid-IR and IR wavelengths, breakdown of dipole approximation has been reported in a number of experiments, most recently in this nice Nature Physics paper. And this is part of the motivation of having a look here at this regime, I think. So in simple terms, this breakdown in this regime at high intensity and low frequency occurs because the laser-induced velocity associated with the quiver motion scales as the field strength divided by omega. And of course, when omega becomes small and E becomes big, this can be a significant fraction of the speed of light, leading to the breakdown of the dipole approximation. Now, in the conventional approach to non-dipole effects, you expand the laser matter interaction to first order and 1OC. But if you do that, you do not actually take advantage of the fact that the external field is strong. And this talk, I'll do that. I'll take advantage of this fact, and I'll introduce an accurate non-dipole strong field approximation Hamiltonian. This is what we call it. And I'll show that this Hamiltonian is accurate and free from certain defects that are present in the conventional 1OC expansion. And I'll then also show that this Hamiltonian is attractive for numerical and analytical modeling. So this is really basic quantum mechanics stuff. We start with the minimal coupling Hamiltonian, where we have used the standard rule of substituting P by P minus QA when we have an external field described by the vector potential A in this case. And I take here eta as omega t minus omega xc. So the laser here propagates in the x direction. And I choose a polarization then, of course, in the YZ plane. If epsilon is 0, it's linear polarized along the x direction. If epsilon is 1, it's circular polarized in the YZ plane. Then I expand the vector potential here to first order in C. It gives me the normal dipole term, and it gives me a correction term. The correction term, in fact, has two terms to it. It has something I call AC and AE, and these two terms are contributions from the variation of the carrier. This is this term which we normally consider, but there is of course also a contribution from the variation of the envelope. But if the pulse has a certain number of cycles, say 7 or so, this contribution here from the envelope is already much smaller than the contribution from the carrier. So in this talk, we'll not be concerned with this latter contribution. Now, with all this, we have the Hamiltonian, which can be written like this: the conventional one, the external atomic and molecular potential, and two correction terms to first order and C, where A1 is the field up here. A problem with this Hamiltonian is that the term proportional to xpz, so it's this one here. You see you have x up here, and here you have p. So if you have linearly polarized along the z direction, you'll have xpz here. This one becomes, of course, non-negligible as x increases, and moreover, this product of operators complicates the practical numerical solution of the Schrödinger equation. So, for example, we cannot use typical split-step fast Fourier transform method. So it would be nice if we could introduce an accurate approximation that brings the Hamiltonian on a form which does not include products of x and pz. And if we look at the Hamiltonian again here, we may already have an idea that if somehow A is sufficient, A naught is sufficiently big, maybe this A naught times A1 is more dominant than this term. So this is the idea. Yes, and the idea is to find such an approximate accurate description first classically, and then after that construct the Hamiltonian. So we look at the classical equations of motion, where we have the Newton equations, including full retardation up here. We have the case where we include retardation to first order. So these are the this E01 and B1 are the fields expanded to first order and 1 over C. And now these 4 lines here describe the scenario, the regime we're interested in, namely a regime where the laser intensity is large and the frequency is small. And therefore it makes sense to consider the effect of the B field component along the E field induced motion. So this is the approximation I want to introduce. So we have here the E field from the dipole part, and then we have here the not the full derivative of the position, but the derivative of the position, oh sorry, the velocity induced by the dipole part of the field. So this is the idea. And then there are some issues here. I put here a factor which should remind us that there is no Lorentz force in this picture for circular polarized fields, because in this case the laser-induced dipole motion is aligned parallel with the B field. And this observation also highlights the sensitivity of non-dipole effects to the polarization of light. So there is a possibility, if we're interested in non-dipole effects, there's a possibility of playing around with the polarization of the light to probe various aspects of non-dipole interactions. So these are the 3 models, and then I want to have a look at the performance of these 3 models. And in this view graph to the left, I have positions in the polarization direction and in the propagation direction, and I have velocities here on the lower graph in the polarization direction and in the propagation direction. In the case of an electron in a laser field of this intensity, 3 × 10⁻14 watts per square centimeter, a wavelength of 3.4 microns. This corresponds to the parameters used in an experiment by the Keller group. And we have here on the x-axis, we have time in atomic units. So for these parameters, this corresponds to 10.5 cycles. Then we have different curves. We have the yellow dotted curve, which is the full retardation model. We have the blue one, which is the first order and one over C model. And we have the long dashed red curve, which is the one I'm particularly interested in here, which includes the effect of the B field along the trajectory induced along the polarization direction from the dipole field. All the trajectories start at the peak of the E field at the exit point, determined like this, and they move in the combined laser field and the Coulomb field after ionization. And from the figures, we clearly see that the approach with this perturbative approach, with this kind of new idea where we have this effect of the B field along the dipole-induced trajectories is very good. You see it's on top of each other, also along the propagation direction here with the exact result more or less. Whereas this one here sets off, and this is due to a breakdown of this 1 over C, conventional 1 over C approximation when X becomes large. So this is very encouraging. So this is, we conclude here that this is an accurate classical approach, and then from this we now go back and construct the corresponding quantum mechanical Hamiltonian. And the recipe for doing this is to look at the Hamiltonian, classical Hamiltonian, which reproduces those classical equations of motions. And you can verify if you use Hamilton's classical equations that the following Hamiltonian does just that. So here is the Hamiltonian, and it's actually the one I alluded to in the beginning, namely the one where the dominant dipole, non-dipole effect is included here in this A0.A1 term. So this is our starting point for this approach, and I call this Hamiltonian the non-dipole strong field approximation Hamiltonian, because we are led to this by including kind of standard strong field approximation arguments. With this Hamiltonian, we have here, of course, something that depends on P, and over here, if you remember, A1 depends on X. So this is in a kind of mixed gate if we follow the standard wording in our field. Because, so you can, of course, now transform X to P or P to X using the standard unitary transformations listed down here. And doing that, you can derive the non-dipole strong field approximation Hamiltonian in the velocity gauge and in the length gauge. And here you have the expressions, and the field is now no longer just A naught, but it's A naught plus a modification determined by this expression here, where you integrate up the Lorentz force. And likewise, if you want to look at it in the length gauge, it's also a modified E field. It's instructive to look at this modification of the vector potential maybe in the infinite pulse limit, where it can be solved analytically, and it's given like this here. So it's a shift in along the propagation direction. If you have electron, the Q is negative, so it's a positive shift. It's like a radiation pressure in the propagation direction. Now, when we have the Hamiltonian, we can go through some of the steps that we like to do, and we always in strong field physics like to have a look at the Volkow wave functions. They can be written up immediately in terms of plane wave paths, which are of course reflecting now whether you are in the velocity gates, the length gates, or the mixed gates. And you also have the phases, which are the Volkow phases now with a non-dipole contribution. And in the long pulse limit, we can evaluate these phases analytically. And we see that we have the conventional kinetic energy, we have the normal UP modified a little bit. That's at least one way to to collect the terms. So we collect terms and introduce something we call UP prime, which depends on the momentum of the ionized of the electron in the propagation direction. And we also have the quiver motion, And we also have this typical term. So this looks pretty much like the standard Volkov phase in the long pulse limit, except that we have U prime instead of U. Now, just in the end here, let me just briefly say that with this Hamiltonian, we now want to apply it. And one of the places where we can apply this and where there are kind of open questions is in laser-assisted scattering, where there has been a problem for many years to have agreement between theory and experiment. And so you have the dipole cross-section for exchange of L photons here expressed in terms of the field-free cross-section, and you have this typical signature of the dressing field, which includes a Bessel function squared and the momentum transfer vector and the viewer motion vector. And the non-dipole, you get more or less the same factorization, except that there is a modification of this Bessel function. It's no longer a normal Bessel function, but it's a generalized Bessel function with two arguments. And it's particularly interesting that the non-dipole contribution introduces a term here which is proportional to the component of the momentum transfer along the propagation direction and not along the propagation direction. So when this argument is 0, this one here is in fact maximum, and therefore this will increase the laser-assisted cross-section significantly in geometries where the standard approach, including only dipole effects, would lead to vanishing cross-sections. So we are working on this at the time being. And of course, we can also look at multiphoton ionization. I've written here the formula for multiphoton ionization in the long pulse limit, including the Fourier transform of the initial orbital and a generalized Bessel function, again modified. It's not UP, but it's UP prime standing here. So we have also looked at the shifts of momentum distributions in the propagation direction. In this Nature Physics paper, there was reported a shift both theoretically and experimentally in the propagation direction, which to leading order can be expressed like IP over 3C. And we find that also with this approach. And of course, this approach can also be used for laser-assisted photoelectric effect, likewise in streaking experiments, where, of course, the non-dipole shift associated with the streaking of the electron would have to be accounted for. If not, one could maybe be led to a wrong interpretation of possible time delays in such studies. So this is
just 1 second.
Yeah. Okay. Anyway, this is a summary, and in the talk I have given a status on the possibility of determining accurate tunneling rates for any molecule which can be treated by quantum chemistry methods by implementing an integral representation of tunneling theory. After that, I discussed some physics related to multi-electron polarization effects in strong fields and turned how a relatively simple procedure can lead to accurate model potentials for single electron dynamics in a suitable modified potential. And this, of course, is very important because it's very difficult for us to do much more than solving effective single electron models. And in the last part, I had some discussion on non-dipole effects in strong field ionization or strong field physics in general at low frequency. And I talked about this non-dipole strong field approximation Hamiltonian that seems to be accurate and attractive for application for linearly polarized fields. Thanks a lot for your attention.
So thank you so much for your nice talk. We have 3 questions which we're going to address. The first one is from Jens Bigert. Lars, is it conceivable with your method part 2 to take a core hole into account, XUV ionization rather than IR, and follow the rearrangement of the screening?
Yeah, I think this is a very interesting question that I would have liked to be able to answer. I think this requires more discussion and thinking that I'm able to come up with right now.
Okay, we have a Slack channel where these questions can be posted and they can be addressed. So we have a second one. Let me see. So from Florian Opperman, how is the cutoff radius chosen for the multi-electron polarization effect?
Yeah, this is chosen on based on classical electrodynamics arguments, simply considering how this bunch of electrons are shifting in the field. So this is detailed in some of. I mean, this with the effect of the effect of polarization and turning off the effective laser electron interaction at short distances was discussed earlier on, and one of the first very nice discussions was from Thomas Barbeck and co-workers, and those references also give a detailed explanation how you can estimate this RC, and you find the references in the paper I mentioned.
And the third and final question is, could you clarify your comment about the delta function in the Lorentz force? We know that the first experimental evidence on non-dipole forward shift was measured with circular polarization. Yeah. So why is this?
Yeah. Very, very good question. So so of course, in general, for the what I call the conventional approach, expansion to
is excluded here.
Okay, you can hear now what I'm saying. I'll try again. So if you follow the conventional approach of expanding everything to first order in C, you can treat any polarization you like. What I discuss here is an approximation to the full approach, and in that approximation, when you introduce this non-dipole strong field approximation, it turns out that there is no effect, there is no non-dipole effect for circular polarization. And this has to do with the type of the interaction, basically that the Lorentz force for circular polar, because the fields are out of phase, basically. So it's a particular thing for this particular simplifying approximation that we have discussed here. For linearly polarized fields, it works. When you start increasing the ellipticity from linear towards circular, this approach that I call non-dipole strong field approximation approach will be gradually worse. How good it performs, of course, depends on the field strength.
Okay, so thank you very much. So for this session, we are running late. Yeah. We are all new on this. So there are quite a few questions and comments on Slack from many people. And let's thank all the speakers and keep watching, because we're starting a battle at 12, which is not a lot of time, but we're gonna have a very quick break and then come back. So also an announcement is that we have also rooms for breaks, and there's going to be a social program which is being organized by Bridget Cooper and Sergei Yushchenko. So first battle starting in 5 minutes. Thank you all so much for joining, and goodbye everyone.